Welcome back to JVM Internals Crashcasts. I'm your host Sheila, and today we're diving deep into the world of synchronization primitives. We're currently in level 3 of our series, focusing on JVM expert topics, specifically in the chapter on concurrency and synchronization. Victor, are you ready to unravel this complex topic for our listeners?
Absolutely, Sheila. I'm excited to explore synchronization primitives with you and our audience. It's a crucial concept for understanding how the JVM handles operations happening at the same time.
Great. Before we start, listeners, make sure you're familiar with basic thread concepts in Java, as we covered those in our previous episode. Now let's kick things off with a quiz question. What JVM feature allows for efficient locking when only one thread is using a synchronized block?
Ooh, that's an intriguing question, Sheila. It touches on some advanced improvements the JVM makes. Listeners, think about how the JVM might handle locks when there's no actual competition between threads. We'll reveal the answer at the end of the episode, so stay tuned.
Now, Victor, let's start with the basics. What exactly are synchronization primitives, and why do we need them?
Great question, Sheila. Synchronization primitives are basic tools provided by the JVM to coordinate access to shared resources when multiple threads are running. They're essential for preventing conflicts and ensuring threads work together safely. Think of them as traffic lights for your program's concurrent operations.
That's a helpful analogy. So, what are the main types of synchronization primitives we should be aware of?
The primary synchronization primitives in Java are locks, semaphores, and monitors. Locks are used to ensure only one thread can access a resource at a time. Semaphores control access to a limited number of resources, and monitors combine a lock with a way to wait for a condition to be true.
I see. Could you explain how these are implemented in Java? I know we use the synchronized keyword, but are there other ways?
Certainly. The synchronized keyword is indeed the most common way to use monitors in Java. It's built into the language and is easy to use. However, Java also provides more flexible options in a package called java.util.concurrent, such as reentrant lock for explicit locking and semaphore for semaphore functionality.
That's interesting. But how does the JVM actually implement these primitives under the hood?
At the JVM level, synchronization is primarily implemented using monitors. Every Java object has an associated monitor, which is used for locking. The monitor is represented in the object header, which contains information about the lock state. When a thread enters a synchronized block, it tries to acquire the monitor for the associated object.
Wow, that's fascinating. So every object can potentially be used for synchronization. Are there any performance implications we should be aware of?
Absolutely, Sheila. While synchronization is necessary for thread safety, it can slow things down. Acquiring and releasing locks takes time, and if overused, can lead to threads waiting for each other and reduced performance. That's why the JVM implements various optimizations, like biased locking and lock coarsening, to minimize this slowdown.
Biased locking sounds intriguing. Can you elaborate on that?
Sure, biased locking is a clever technique where the JVM assumes that most locks are only accessed by a single thread. It biases the lock towards that thread, allowing it to enter and exit synchronized blocks more quickly. If another thread tries to acquire the lock, the bias is removed, and the JVM goes back to standard locking mechanisms.
That's clever. It reminds me of how we might give a regular customer at a store preferential treatment. Now, what about best practices? How can developers use synchronization primitives effectively?
Great analogy, Sheila. As for best practices, there are several key points to remember. 1. Use synchronization judiciously. Only synchronize where necessary. 2. Keep synchronized blocks as short as possible to reduce waiting time. 3. Consider using higher-level tools from java.util.concurrent when appropriate. 4. Be aware of potential deadlock situations and design your code to avoid them. 5. When possible, use immutable objects to eliminate the need for synchronization altogether.
Those are excellent tips, Victor. Now I'm curious about how synchronization primitives in Java compare to other languages or platforms. Any insights?
That's a great question. Java's synchronization primitives are quite similar to those found in other languages, but there are some differences. For example, CTARS has a concept called lock, which is similar to Java's synchronized keyword. Python uses a different approach called the global interpreter lock. In general, Java's implementation is known for being robust and well optimized, especially with the continuous improvements made to the JVM.
Fascinating. It seems like there's always more to learn about synchronization. Before we wrap up, let's reveal the answer to our quiz question. Victor, would you like to do the honors?
Of course. The JVM feature that allows for efficient locking when only one thread is using a synchronized block is biased locking, which we discussed earlier. It's a great example of how the JVM optimizes for common usage patterns.
Thank you, Victor. To summarize today's episode, 1. Synchronization primitives are essential for thread safety in concurrent programming. 2. The main types are locks, semaphores, and monitors. 3. Java implements these through the synchronized keyword and classes in java.util.concurrent. 4. At the JVM level, synchronization uses object monitors and lock information in object headers. 5. The JVM employs optimizations like biased locking to improve performance. 6. Best practices include using synchronization carefully and considering higher-level concurrency tools. In our next episode, we'll be diving into the Java memory model in depth, which builds on the concepts we've discussed today. Don't forget to subscribe and rate our podcast if you found this information helpful. Until next time, happy coding.